So far, we followed a request from your phone across the internet. We talked about networks, routers, switches, protocols, the internet infrastructure, but now we're going to zoom in much closer. What actually happens to the data itself as it travels across the network? How does your computer package information? How does the internet know where to send it? How does Google know where to send the response back? To answer those questions, we need to talk about one of the most famous concepts in networking, the OSI model. The OSI model is not a machine. It's not software. It's not hardware. It's a framework and a way to understand how networking functions are divided into layers. And honestly, without layers, networking would become absolute chaos. Imagine mailing a package. You don't personally pave the roads. You don't operate the delivery truck or build the sorting facilities or manage the air traffic control and fly the airplanes. Different systems handle different responsibilities, and networking works the same way. Different layers handle different jobs. And by separating responsibilities into layers, systems become easier to build, easier to troubleshoot, and easier to standardize. The OSI model is basically networking's organizational system. There's seven layers to it. And yes, people invented ridiculous mnemonics to try to memorize them. You'll probably encounter, please do not throw away sausage pizza. I apologize in advance on behalf of the networking industry. But the important part is not memorizing names. The important part is understanding the flow. Data starts at the top layer, the application layer, then moves downward through the stack, and eventually it becomes electronic signals, light pulses, or radio waves moving across the network. Once it gets to the destination, that process reverses. Data climbs back up the layers until the receiving application can use it. These top layers, those are closest to the user experience. But think of application layer. That's Chrome, Discord, Spotify, YouTube, Zoom, all that good stuff, right? The application layer handles communications between software applications. The presentation layer handles things like formatting, encryption, compression, and the session layer helps maintain communication sessions between systems. Now, here's the important thing. In real world networking, these layers often blur together. Modern operating systems and applications combine many of these responsibilities automagically. But conceptually, these layers help us understand what's happening behind the scenes. The transport layer. This layer is incredibly important. This handles end-to-end communications between applications, and this is where we encounter TCP and UDP. TCP is reliable. It checks, did the data arrive? Was anything lost? Should something be resent? TCP is kind of like certified mail. It's reliable, tracked, confirmed. That reliability is extremely important for things like banking, file downloads, websites, authentication. UDP is different. UDP prioritizes speed over reliability. No confirmation, no guaranteed delivery. It sounds bad at first until you realize speed matters for certain applications. For example, gaming, voice chat, live video streaming. If a single voice packet gets lost during Discord, you probably won't notice, but waiting for retransmissions could introduce lag. That's why UDP exists. Let's test. You can test connectivity using ping. You can open up terminal or command prompt and type ping space google.com, and you will see packets being sent and responses returning. You'll also see latency, the time it takes for packets to travel across the network and back. That's real network communications happening live. What's the difference between TCP and UDP is a really, really great interview question. Something you should definitely write down. The network layer is responsible for moving data between networks, and this is where IP addresses live. An IP address is basically a network location. Think of it like a street address. Routers use IP addresses to determine where traffic should go. As your data travels across the internet, routers continuously make forwarding decisions. Where should this packet go next? What's the best available path? How do we reach the destination? That routing process is happening constantly over the internet. If the IP address is a street address, MAC addresses are more like apartment numbers. A MAC address identifies devices on a local network. Switches use MAC addresses to deliver information locally. This layer is heavily tied to the physical hardware. This is also where Ethernet operates. One important thing to understand, MAC addresses generally stay local. IP addresses help move traffic globally. And MAC addresses help move traffic locally. At the bottom of everything, networking becomes physics. The physical layer is responsible for transmitting raw bits. That transmission might happen through copper cables, fiber optic, radio waves, wireless signals. Fiber optics are especially fascinating because they use pulses of light to move enormous amounts of data incredibly fast. And modern internet infrastructure relies heavily on fiber because the bandwidth requirements today are just absolutely massive. And encapsulation, this is one of the most important concepts in networking. As data moves downward through the OSI layers, each layer adds information. Headers get added, addresses get added, control information gets added. That data becomes incredibly packed or increasingly packed for transport. Eventually, data becomes segments, then packets, then frames, and then bits. Once it gets to the destination, that process reverses. This layered packaging system is one of the reasons networking is so flexible and scalable. And one of the biggest reasons networking professionals learn the OSI model is for troubleshooting. Imagine if someone said, hey, Blackboard won't load. Where do you even start? Is it the Wi-Fi? Is it DNS? Are there browser issues, routing problems? Is the ISP out? Is the firewall being silly? Are there server problems? The OSI model helps technicians isolate problems logically. CompTIA teaches a 7-step troubleshooting process. Identify the problem, establish the theory, test the theory, plan the fix, implement the solution, verify functionality, document findings. And honestly, a huge portion of IT work is troubleshooting. So if you type something, you bring up ping and you type Google, but with one O.com, what happens? Do you get a response? Is that a DNS problem? Is it a network problem? Troubleshooting often is about eliminating possibilities systematically. So across these 3 videos, we followed on one simple question: what happens when you open YouTube? And along the way, we explored networks, protocols, hardware, routers, switches, LANs, WANs, the internet, the OSI model, TCP/IP, and troubleshooting. The internet is one of the largest and most complicated systems humans have ever built, and underneath all that complexity are surprisingly understandable ideas. Devices communicating through agreed upon rules across interconnected networks. And throughout the rest of this course, we're going to keep building on those foundations. IP addressing, routing, switching, wireless networking, security, troubleshooting, and eventually real-world networking infrastructure. Because once you understand networking, you start seeing the invisible systems powering the modern world everywhere.